In this section, we're talking about the derivatives of exponential and logarithmic functions, and we've seen the derivative of y equals e to the x power, which is one specific exponential function, and y equals natural log of x, which is one specific logarithmic function. Now, these are by far the most common cases that we are going to see. When we're working with exponential functions, it will almost certainly be e to the x, probably 98% of the time. But we could have other bases for both our exponential and logarithmic functions. We could have, say, like y equals 2 to the x power, or y equals log base 2 of x. And we should know how to take the derivatives of these functions because we may run across them from time to time. So the derivative rules for these are a little bit more complicated than just e to the x and natural log of x, but they do look really similar to their counterparts. So first we'll talk about exponential functions. It says the derivative of f of x equals b to the x power is f prime of x equals b to the x power times the natural log of b. Hopefully we can see a little bit of similarity between this and the derivative of e to the x. When I take the derivative of e to the x power, I end up with y prime equals e to the x. And when I take the derivative of something that's, let's say, base 2, or let's say base b here, when I take the derivative of b to the x power, well, I get back that same b to the x power just like I did with e to the x, right? The derivative of e to the x was just e to the x. So we get back that b to the x. We are just also going to have this extra natural log of b that we need to multiply it by. So that's really the only new addition to this derivative rules. We are multiplying that by the natural log of b. Same similarity, or another similarity we'll see is with the logarithmic functions. If I'm working with log base b of x, that derivative is going to look like g prime of x is 1 over x times natural log of b. And hopefully we can see a little bit of similarity with the derivative of natural log of x. That derivative looked like 1 over x. And when I take the derivative of a logarithm with a different base, in this case log base b, hopefully we can see that 1 over x appearing in our derivative again. We are just going to also, in this case, divide the result by natural log of b. So in exponential functions, we are multiplying by the natural log of b. In logarithmic functions, we are dividing by natural log of b. Other than that, they're going to look very similar to the derivatives of e to the x and natural log of x. So we'll work through a few examples here. First example, I want to find f prime of x for 2 to the x power minus 3 to the x power. So if we need to, we can scroll up and we can peek at that derivative rule. F prime of x equals b to the x times natural log of b. So when I find f prime of x here, the derivative of 2 to the x is going to be 2 to the x power times natural log of my base, which in this case is 2, minus the derivative of 3 to the x power. And if I want to, again, I can think about it like e to the x power. The derivative of e to the x power is e to the x. The derivative of 3 to the x should be 3 to the x. I'm just going to have to multiply by an extra natural log of 3 at the end here. And there is my derivative. I don't really need to do any simplifying or anything past that. There's my derivative. Next up, I've got f of x equals log base 4 of x minus natural log of x. So here I have an exponential, or excuse me, a logarithmic function of base b, so I can scroll up and look at this derivative rule here if we need to. So g prime of x is 1 over x times natural log of b. So here, f prime of x, derivative of a logarithm, well, that's going to look like natural log. So that's going to start off as 1 over x. I just need to also divide this function by natural log of my base. In this case, that's going to be a natural log of 4. Minus the derivative of natural log of x, well, we know that derivative, it's just 1 over x. If you really feel like it, you could find a common denominator, but I think that's a perfectly fine place to stop then after that. Last example that we'll, actually 2 more examples that we'll look at here. G of x equals log base 8 of x minus log base 5 of x to the 6th power. This first term is going to be relatively straightforward. We're going to use that, that new formula that we just talked about a second ago. Here, though, this one's a little bit tricky. We do want to use that formula, but if you look at what's inside, here we've got x to the 6th power is inside of our logarithm function. And we don't know how to take the derivative unless the inside is just x. So we're going to have to use those log properties that we talked about in the last video. And those log properties, I gave them for natural log of x because that's the most common case that we're going to run into. But we will, all those log properties do apply for any logarithm. So I can apply those same logarithm properties. First term, okay, don't need to change anything. Log base 8 of x minus that second term there. I can rewrite this exponent, this power, as a factor, and I can write that as 6 times log base 5 of x. Now this is something that we know how to take the derivative of. The inside part of the logarithm functions are both just x, so we should be good to go at this point. So g prime of x log base 8 of x. So that's going to look like the derivative of natural logarithm. It's going to look like 1 over x. I just need to also divide that by the natural log, the natural log of whatever my base is. In this case, it's an 8. So I need to divide by natural log of 8. Minus 6 is a constant multiple, so I'm going to multiply that by my derivative. Here I have another logarithm, so its derivative is going to look like the natural log, 1 over x. I just need to also divide that by natural log of my base, which here is 5. So have a natural log of 5 in my denominator as well. And if we want to, we can clean up that second term. I'm going to rewrite this as 1 over x times natural log of 8 minus 6 over x times natural log of 5. And there is my derivative. Our last example for this video here, I have f of x equals x to the 10th plus 10 to the x power minus 10 times e to the x power. So the first term, f prime of x, x to the 10th power, well, that's just a regular old power rule. That's going to be 10 times x to the 9th power. Here I have 10 raised to the x power. This is an exponential function, so it's going to look like the derivative of e to the x. So that means I'm going to get the same function back. I'm going to get 10 to the x power. I just need to multiply that by natural log of my base, and in this case, my base is 10. So I need to multiply that by natural log of 10. Minus, for my last term, the derivative of negative 10 e to the x. Well, that's going to be minus 10 e to the x. So there is our derivative. So these derivatives, or these functions, while they do have different derivative rules, they are very, very similar to y equals e to the x and y equals natural log of x. Like I said, 98% of the time, we're going to be working with those base cases, y equals e to the x and y equals natural log of x. But every now and then, we will run into a function that has a base of other than e.